Hello, everyone. I'm Xiaohan Duan from Cooperative MediaNet Innovation Center, Shanghai Jiaotong University. The title of my paper is Non-Equiprobable Non-Uniform APSK Constellations Design for BICM Systems. There are 5 parts in my presentation. The first part, background. Bit interleaved coded modulation system is widely used in modern communication. In the BICM system, bit interleaver between a FEC code and a modulation module guarantees that symbol demapping can be decoupled from channel code. This feature ensures the independence of each module and facilitates the design of the BICM. BICM is adopted in many advanced broadcasting standards such as DVB-T2 and APSK 3.0. Considering modulation of BICM system, there is a gap between capacity of uniform QAM and the channel limit. In other words, the conventional QAM constellations cannot meet the increasing demand for the data volume in modern communication systems. Adopting higher modulation order and spacing constellation symbols non-uniformly are two strategies. The study of constellation design focuses on the trade-off between performance gain and demapping complexity. Neither 2D NUC nor rectangular 1D NUC is able to satisfy the requirements, especially for high orders. So our goal is to reduce the demapping complexity with almost no performance degradation. The second part, NUCs. Non-uniform constellation is the key technology to reduce this gap to channel limit. Constellation symbols of NUC are non-uniformly spaced on the complex plane, so NUC can provide more shipping gain. NUC has been adopted in DVB, NGH, and APSK 3.0. There are 2 types of NUCs. One-dimensional NUC keeps in the rectangular shape but doesn't have equal distances between adjacent constellation points, while the other two-dimensional NUC is more flexible and with no fixed shape. Paper 1 uses APSK as the initial constellation to obtain NU APSK. NU APSK still remains its round shape and has both better performance and lower demapping complexity. The third part, proposed design method. By observing NU APSK, we can see that there are some points close to each other. According to Paper 1, the average Euclidean distance is increased by using one coordinates corresponding to multi-labels. Here we propose 2 design schemes. Scheme 1, first according to this formula, obtain the optimal set of radius which follows Gaussian distribution, and then find out the optimal PSK order for each radius which makes BICM AMI maximum. The third step is to optimize the constellation using the PSO algorithm. Scheme 2, first use the PSO algorithm to obtain NU APSK and then merge adjacent points in the above obtained non-uniform equal probability constellation. Since the radius set of method 1 is not necessarily the optimal set and the design freedom is method 2 is greater, method 2 is chosen. The specific merge method is as follows. For any point xn belongs to chi, the Euclidean distance between them is expressed as formula 1. For points on different radius, the distance must be lower than the limit. This limit, and for points with offset phases theta m and theta n respectively, on the outermost radius are max, the physics must satisfy this formula. Here we gave the analysis of the demapping complexity for a constellation of order m. The demapping complexity is the half m power of 2 for 1D NUC, and the half m minus 1 power of 2 plus the half m minus 1 power of 2 for NU APSK in the APSC 3.0 standard. The demapping complexity of NU APSK is less than NU APSK because there is a merging of points. The fourth part, simulation results. In the simulation, we choose LGBC with a length of 64,800 and test constellations with the order of 1,024 and 4,096 at 3 code rates of 3/5, 4/5, 3/15, 4/15, and 5/15. We choose the scheme 2 mentioned above. The simulation is conducted in AWGN channel 1D NU-COM adopted by APSC 3.0 and NU APSK are selected to be benchmarks. Figures shows the performance comparison of our design in NU APSK with 1D NUC and NU APSK. Specifically, the x-axis is the SNR value and the y-axis is the BR value in the range of the negative 6.10 to 0.1. It can be seen that the design in NU APSK with the order of 1,024 and 4,096 both have gains relative to 1D NUC in APSC 3.0, while the performance loss is minimum compared to NU APSK. In this table, specific experimental results data are given. Gains indicates the performance gain of our design NU APSK to 1D NUC, and loss indicates the performance gain of our design NU APSK to NU APSK. At the same time, we make the demapping complexity decrease with essentially no performance loss. It can be seen that the lower the code rate is, the more the demapping complexity is reduced. Finally, the conclusion is that in this paper, a well-performed constellation called NU APSK is proposed. Simulation shows that NU APSKs with order of 1,024 and 4,096 at a code of 3/15 to 5/15 all have BR performance gain compared with the 1D NUC in the APSC 3.0 and have a comparable performance to NU APSK. In terms of demapping complexity, our designed constellation has up to 84% reduction compared to 1D NUC and up to 87.5% reduction compared to NU APSK. That's all. Thank you.